So, the unit circle. So what is going on with this special circle here? And why do we care about it? So, the unit circle, the reason we care about this is it helps us actually find the exact values of some certain trig ratios that otherwise would not be possible. And it kind of lays it out in a simple format so that we don't really have to worry. So, you have this circle here, and it's drawn on this Cartesian plane where we have an x-axis and a y-axis. And we're not really caring too much about like necessarily it being a graph. We're just looking at the points of intersection between our hypotenuse and the edge of this circle. So if I were to draw something like that, we're looking at this coordinate point right here. And that actually helps us find our trig ratios, as you'll see later. So if we take a look at this intersection, there's three intersections that we're actually going to take a look at. And one thing you got to know with the unit circle is that the radius all around, like the radius of this circle, is going to be 1 unit. So if I were to draw this line here, so this white line that I've drew that has intersected the circle, this would be 1 unit. And I'll just put 1 for now because it doesn't really matter, but it is 1 unit around. And if I were to draw another line like this would be 1 unit. So the hypotenuse, if you want to look at it like this, would be 1 unit. Because if you think about this, we're making this triangle here, and this would be the hypotenuse. The radius would be the hypotenuse. And we make a triangle that looks like this. Our 90 degrees would be here, and our reference angle would be right here. So we have 3 triangles that we care about, and these happen to be these special triangles. The special triangles that we learned about, which are the 30-degree triangle, the 45-degree triangle, and the 60-degree triangle, which are special in Math 20. And I'll show you why. So normally, when you have the 30-degree triangle, what you do is you draw it like this, right? You draw something that looks like this, and then you have 60 degrees at the top. And then you would label it from there. You would go like this, and 1/2, and then 1. And it's kind of a bit of a hassle to actually find some trigonometric ratios by doing this. So the way the unit circle actually comes in, and the way it actually helps us, is it lays it all out. Like, it's very simple here. So if we were to draw this, the 30-degree triangle would be our first one, since it's our lowest angle. So our 30-degree triangle would look like this. It's not going to be perfect, not necessarily, but 30 degrees. And we got to think about this. Since we're on a Cartesian plane, the height of this triangle, or this side right here, the side opposite to our 30-degree angle, is going to be y. So we have the coordinates where y is our opposite side, which is going to be relevant later. Now we have our distance from the origin point to this point, and that can be labeled as x. So we're laying out our simple trigonometric stuff and trigonometric functions in coordinate point form. So it's really cool. I'll show you. So, and this x point here would be the adjacent side, since it's adjacent to this 30 degrees here. So this some of the math 10 stuff here. But yeah, so we have the adjacent and the opposite side as y. So the adjacent side would be x, opposite side would be y. And that's really helpful, and I'll show you again why later. So if we were to think about this coordinate point here, if we're labeling this triangle normally, right? This side here would be √3, or no, sorry, this side would be 1/2. And then the one across from 60 would be √3/2. And then your x would be √3/2, comma, 1/2, as a coordinate point laid out like this. But there's actually an easy way we can actually label all 3 of our special triangles here. So if you're asked on a quiz or anything to label the special triangles or label your coordinates points of a unit circle, here is one of the ways you can do it really fast. So let's say we had this point here, which created a 45-degree angle, and then this point here, which created a 60-degree angle. And you're asked to find the coordinate point for x and y for each of the following points, or each of the following angles. So the way you do this is starting in ascending order from x, you're going to go up 3, 2, 1, and then descending from y goes down 3, 2, 1. You're going to divide everything by 2. So every number you're dividing by 2. And you're going to put a square root sign in front of every numerator, except 1, since the square root of 1 is simply 1. So you're square rooting every single numerator here. And what you've done is you've successfully labeled each of the following triangles. You've labeled every single coordinate point on quadrant 1 here. Duly noted, this point here, which intersects, would be a where x is 1, 0, and this y point here would be 0, 1, as it is 1 unit up from the point of origin, and this one here is going to be 1 unit right from the origin, so that's why it's positive 1. Now, if we were to go to this side, this would be 180 degrees over here. 180 degrees technically, if we think about this as a standard angle. This would be 180 degrees. And this coordinate point for 180 degrees would simply be -1, 0. Reason being, we're going left 1 unit, and we're not going up or down in any way. We're staying on our y-axis, but we're going left 1 unit. So that is a horizontal translation, and when you're translating left, that's negative, right? Now for this final unit down here, same thing. We're going down 1 unit, which means we're going to have a negative y, so -1y, and we didn't move left or right, so our x translation stays the same. So we have no movements in terms of x from that point. So it's going to be 0, -1. And if you're wondering, this would be 270 degrees right here, if we're thinking about it in relation to a standard angle, right? So this full turn would be 90 degrees. This full turn would be another 90, which is 180, and then another 90 would be 270, which brings you back to there. Now that we've actually covered and labeled all our points on our unit circle, how does this actually help us, right? So how the heck does that help us with our trig ratios? So if we use our SOHCAHTOA definition of trig functions, so SOHCAHTOA, we've learned this from Math 10. This helps us find the sides and determine the trigonomic ratios of a triangle, right? So SOHCAHTOA, the SOHCAHTOA definition. So sine is stated that the opposite side over our hypotenuse is equal to sine theta. So sine theta is equal to opposite over hypotenuse. And it's nothing new here, like we know this, but all we're doing is we're putting it in relation to this unit circle. So we have sine theta. So if we're asked to find sine of 30 degrees in the exact value, what can we do here? Well, we have sine of 30. So we look at our 30-degree triangle here, and we look at the opposite side. Remember, the opposite side is going to be our y value. So we have 1/2, and we're going to divide that by our hypotenuse. But notice how our hypotenuse is 1. If we were to try this, we have y, which is over 1. Our hypotenuse is always 1. So if you think about this, when you're dividing by 1, nothing changes. So in this case, sine theta in our unit circle is equal to the coordinate of y. And that's all you got to know. If you're looking for sine of any angle in the unit circle, all you got to look at is the y value. So let's take a look at this. So let's say we were looking for sine of 90. Sine of 90. So 90 degrees is formed over here. And we're looking at this coordinate point, 0, 1. Notice how the y value is 1. So does that mean sine of 90 is equal to 1? That does. That's it. That's how you do this. Now let's try sine of 45. Sine of 45 degrees. We look at our 45-degree triangle, and let me change colors. It's getting a little hectic here. But sine of 45 degrees, right? Our coordinate point is going to be root 2 over 2 for y. Does that mean sine of 45 is equal to root 2 over 2? Oh, yes, it does. Because if we were to divide by our hypotenuse, which is 1, that changes nothing. Now, let's take a look at cosine. So cos theta is equal to our adjacent side, which is over our hypotenuse. So that's equal to x over 1. Our hypotenuse is 1. And remember that our adjacent side is going to be x, because that's the side where it's adjacent to the angle. So x over 1. When you divide by 1, that's nothing. That doesn't change anything, right? So cosine theta in the unit circle is just equal to the x coordinate. So let's look at the x coordinate. So let's say you were asked to find cosine of 30 degrees. Cosine of 30 degrees. So the way you do this normally is you'd probably draw out this 30-degree triangle, right? So 30 degrees, and you have 60 degrees, and you have 90 degrees, and then you have to do this, and no, we don't have to do all that. We look at our unit circle, which we've beautifully labeled, by the way, and we look at our 30-degree triangle here. So 30 degrees right here, and we look at our x coordinate. Our x coordinate is root 3 over 2. We're done. That's how you find the exact value trigonomic ratio. You're done. You've done it in 3 seconds. Now, let's say you were asked to find the cosine of 60 degrees. So we look at our 60-degree triangle. Our x coordinate is 1 over 2. And if you were to put it in your calculator, you put cosine of 60, and that's equal to 1 over 2. So we found a quick method for finding trigonomic ratios using the unit circle super easily and efficiently. So now that we've defined cosine theta, which is equal to x, if we think about this, and sine theta, which is equal to y, we can use this. So we haven't discussed tangent. We haven't discussed tangent yet. So where does tangent come in? So if we think about tangent, so tan theta. What is tan theta? So tan theta, according to our SOHCAHTOA definition, is our opposite over adjacent. Or in other words, our opposite, remember, is going to be the y coordinate over adjacent, which is the x coordinate. And we've defined cosine theta as x and sine theta as y. So this, in other words, could be written as sine theta over cosine theta, which is equal to our tangent. Tangent theta. Depending on how you want to write that, but the easiest way that I like to remember it is y equals, or y over x is equal to tan theta. The reason I mention this is maybe it might pop up one of your quizzes and true or false or whatever, or match which of the following is true about tan theta. Tan theta is equal to sine theta over cos theta. So they're equivalent, okay? So now, if we were asked to find tangent of 45 degrees. So we look at our 45-degree triangle here, and our x value, or x coordinate, is root 2 over 2. So root 2 over 2 divided by our y coordinate, was root 2 over 2. And our x coordinate in this case is going to be root 2 over 2 as well. So root 2 over 2. You're dividing a number by itself, that gives you 1. And if you were to put tan of 45, notice how it's equal to 1. So now we've actually found a simple way to actually find the exact values of these trigonomic ratios really easily, right? So let's say we were looking for tan of 240 or 270 degrees. So the way you do this is you infer to your unit circle here. We had 270 degrees as 0, -1. So, and we said that tangent is equal to y over x. So we have -1 over 0. And if you were to put that in your calculator, what does that give you? That gives you undefined. If you were to put tangent of 270, notice how it's undefined as well. So this explains why some trigonomic ratios are going to be undefined. It's a cool way. It just works. Now, let's say you were asked to find a weird angle. So let's say you're asked to find sine of 180 degrees. So 180 degrees, right? You're probably thinking still a little unorthodox, and you have to find the reference angle here. So just remember we're working with right triangles here. So we're not going anything past right triangles. This circle works such that each quadrant is its own different right triangle. So if we're thinking about this, if we have 180 degrees over here, or sorry, if this was sine of 210 is what it should be. Yeah, if this was sine of 210, if you think about this, the way we find our reference angle is we subtract 180, and you get your reference angle equal to 30 degrees. So you're looking for your reference angle. So 30 degrees. You're working with a 30-degree triangle when you have 210 degrees. So it's the same thing. This is going to be same coordinate. So if we look from earlier, how do we label this? So we had a 30-degree triangle. The x value was root 3 over 2. And the y value was 1 over 2. You're just taking the exact same thing, and you're going to change it into respect on where it is on the graph. So we're in quadrant 3, meaning that our x values are going to be negative, and our y values are going to be negative as well, since we are going under the x line and under the y line. So that's all you're doing. You're doing the exact same thing. So now sine of 210, what do we say that was equal to? We said the sine of 210, or sine theta, was equal to y. So if we look at our y coordinate, sine of 210 degrees is going to be equal to our y here, which is negative 1 over 2. And if you were to put that in your calculator, sine of 210, look what that gives you, negative 0.5. So now let's final example. Let's try this out. Let's say you were to ask to find the coordinate point for the angle of 300 degrees. You're asked to find the coordinate point for the 300 degrees. So again, well, all we're doing is we're finding the reference angle, right? So we're going to subtract 360 from 300 degrees, and that gives you a reference angle of 60 degrees. Cool. Now that we've found our reference angle of 60 degrees, what can we do with this? So one cool thing we can do now is we look at our 60-degree triangle. Our x coordinate was what? Was 1 over 2. Our y coordinate was root 3 over 2. And just remember the way that we actually name this through the 3-2-1 method. Divide by everything by 2, square root the numerators, and you'll get the exact same thing. Once you've labeled one triangle or one quadrant, you can label every other quadrant. So now you have 300 degrees, and let's say you were asked the cosine of 300. Remember that we defined the cosine equal to our x-coordinate, so our x-coordinate here is 1 over 2. But remember one thing. What do we need to change here? We need to change, since we're in quadrant 4, our x values are going to be positive, but our values are going under the y line, so we have to make sure that our y value is negative. No, doesn't affect our cosine, because since it's equal to x. So if we were to do cosine of 300, notice how it gives you 0.5. I know it was a lot. It was an information dump, but this is a conceptual overview of the unit circle. Hopefully this video helped you understand it a little bit better, and hopefully you can apply it into some of the ways you actually find the exact values of. If this video helped, just let me know, and leave a like if you can. It really helps out.